Hello, and welcome to Aggressive Physics. Today is day 20, and what I want to do is look at graphical analysis of motion examples. Now, many of us are going to be able to find the slope or the area pretty easily. We've done this in math class a number of times. And to find the slope, it's change in y over change in x. And to find the area, it's either going to be base times height or 1/2 base times height. If we have a complex shape like a trapezoid, we'll break it into an 1/2 base times height, a triangle, and then add that value to base times height. If it's above the axis, they're going to represent positive numbers. If it's below the axis, it'll represent negative numbers. If we're trying to find displacement, we may add a bunch of positives and negatives and find that the displacement of the object is actually 0. All of our graphical representations are identical to the equations that we've been using already, but just give us a different point of view, a visual representation of the motion that may allow us to estimate what's happening a little quicker, come up with our own version of a story that represents the motion. Now, what I think is important is that we also understand it qualitatively. Quantitatively, using numbers, we're okay with. Sometimes the numbers are a little hairy. They're a little different than a math class where everything seemed to be nice and easy when you're starting off. When you're dealing with real data, sometimes the numbers are not as pretty. They're not as easy to deal with. They may have exponents that are 10 to the negative something. Well, it's one thing to be able to calculate an answer. It's another thing to really understand what's going on. And what I want to do is spend today going through a number of examples of what the graphs will look like for displacement versus time, velocity versus time, and acceleration versus time with different scenarios. We'll start with single segment graphs, and we'll move on to more complex graphs where we have 2 segments. We could add 3 or 4 if time permits, but I think we'll stick to single and 2 segment graphs. Now remember, displacement versus time graphs have to be continuous. You cannot have a displacement time graph that breaks in the middle, because what that represents is that an object warps from one position to another in a fraction of a second. That's impossible today. We don't have warp technology or transporting technology like we may have in the future or like we have in science fiction. So if you're doing a displacement time graph, it has to connect from one segment to the other. The velocity versus time and acceleration versus time, assuming that the changes occur instantaneously, can be inconsistent. You can have a break in the graph and basically have steps that represent the motion. So what we're going to do today is just look at a number of examples where we have different motions and what do the graphs look like for velocity versus time? What do the graph look like for acceleration versus time? What will a graph look like if we take a specific graph and look at the next spots? We're not going to calculate anything. We're just going to analyze what they would look like qualitatively, not quantitatively. So let's see a couple of examples now, and we'll complete the end of our discussion of graphical analysis. A very quick chapter, but one that's important nonetheless. What I'd like to do now is see if we can take the initial graphs of displacement versus time and draw the graphs for velocity versus time and then acceleration versus time for each of the graphs. Now, these objects are A, B, and C. And what I'll show you is that each of the graphs can represent the same object but look radically different. In fact, it's important to realize that although a velocity graph may look like a straight line, the displacement graph could actually be curved. And as we move down this list from D to V to A, remember, as we move down, we are finding the slope. As we move back up, that's using the area. So we have the slope being moved downward and the area up. If we had our mnemonic where this was S instead of D, it would be SVA, AVS. SVA, slope, AVS, area. Now, this shows a curved displacement graph, which means we have a positive acceleration. And what we could do is merely just start with this. There's our acceleration. What's the acceleration on the second graph? It's not a curve. So we know that it has no acceleration. So actually, the acceleration graphs are going to be easy to start with. Displacement there is flat. It means it's not moving for object C. So the acceleration is flat. 0 as well. So even though these two graphs B and C have the same acceleration, the graphs on the displacement actually look different. And this is why it's hard to use the acceleration graphs for any useful knowledge moving back away from the acceleration. That's why typically the V graph is the most important, because you can go either way. You can either find the area and get the displacement, or find the slope and get the acceleration. Now, what's the velocity at the beginning? It looks like it's fairly flat, so it's going to be 0. What's the velocity as we move forward? It gets more positive as we move along. So the velocity graph for the first one would have something like this. Now, doesn't that make sense then that the slope of this is positive? And we end up with an acceleration that's above the axis. Well, it should. Slope of that is a positive A. It's a positive A. Notice we've used no numbers here. Now, for the velocity graph here, what do we know about the slope of this? It's going to be positive. We don't know a number, but it's positive. So the velocity will be positive. And the slope of a flat line is 0. Now, what's the slope of that line? The velocity is 0. This object is stationary. So we have 3 different objects, A, B, and C, each with radically different displacement, velocity, and acceleration graphs. Now, if you use a motion sensor, or if you use a program that will allow you to collect data in real time, what you'll find is that the computer will often give you the displacement graph and the velocity graph. But since the acceleration graph doesn't yield too much useful data, and also in the real world it would be very spiky, even at 0 it would probably be spiky a little bit, because real objects don't actually have 0 acceleration, or I'm sorry, positive acceleration for this one, or exactly 0. We'd find that it's easier to use these top 2, or more apparent what is happening in the object's motion. So this shows 3 objects and their displacement, velocity, and acceleration graphs for each. This object accelerates, object A. Object B is traveling at a constant velocity. And object C is the most boring of all. It's just sitting there. Object C is our sloth. All right, let's look at a sample problem here where we have an object traveling with 2 different distinct types of motion. In this case, from 0 to A, we have a curve, and then from A to B, it appears to be a straight line that's flat. Now, you can treat each segment as a separate problem. This straight line and the curve are 2 different things. And since we've already discussed different types of graphs that can be created from the curves or straight lines, we should be able to take our information from that and just combine it for each individual thing. Just like any problem, we're taking a complex situation, in this case 2 segments, and treating it as a series of 2 independent single segments. Now, a single segment is easier to deal with than 2. So if we treat each as an independent one, we then can combine the answers and understand the object's motion in its entirety. Now, the way I'm looking at this, I can see that the object is traveling at a positive velocity to start. It is slowing down as I hold my marker along the curve. It's decreasing its slope, and then it is stationary. So I know immediately that the velocity between A and B for the second segment is going to be 0. And because it's a straight line over there, I'm going to say that the acceleration is also going to be 0. Now, the velocity goes from a positive to 0. And since we have a curve, it's going to be a straight line downhill velocity. It's decreasing and it stops. Now, what does a negative slope mean? It means your acceleration is negative, but it's constant. It's uniform. So what we have is a situation where the acceleration is negative here, and the slope here is negative, and that's why the acceleration is below the axis, because the slope of the velocity time graph gets me the acceleration. So in this case, this looks a little weird. It's like a line graph bar graph actually. The reality is this here probably wouldn't go from an acceleration that's negative to 0 instantaneously. There'd be some kind of spike in a real graph. But for this purpose, we're going to treat it as an ideal situation. It goes from a positive, there's 0. And if we look at each segment individually, this shows no motion, V was 0, A is 0. This shows a curve like that, downhill, negative acceleration. So that's how we can deal with a 2-segment graph. I think we'll look at one more. Now, because curves are often our more difficult shapes to analyze, what I'd like to do is look at a curve for each segment. So we'll have a curve that curves up, and then a curve that curves down like that. Almost makes a flattened S or something to that effect. We'll say that point A is where it switches from the up curve to the down curve. Now, just looking at this, we realize that it's accelerating the entire time, but the acceleration is going to change. In fact, what do I know about the value of the acceleration for the first segment? And we need to label A and B for each. Now, the reason these graphs look slightly different than what I drew before is because I know that some of the velocities are going to be positive and negative, and the same for the accelerations. So you'll often see the velocity time graph not drawn with the origin at the bottom, but the origin in the middle, so that you can have both positive and negative values. The same for acceleration. Now with this, if I use my cup test where I put my hand along the graph, I know that the first segment has a positive acceleration. For the second segment, it's falling out of the water, so it's a negative acceleration. So I could just jump straight to my acceleration graphs. I have an acceleration that goes like this, positive, then jumps right down and becomes negative. So this here is my positive acceleration, this here is my negative. And I know I drew one below the other, but it's typically a, they'd probably be in this case, the fact that the curves are similar, they'd probably have the same height. So the reality is I probably should draw this one a little bigger. There. Something like that. Now, this part here would, in reality, show spikes probably. We're treating it as if it can go directly from positive to negative instantaneously. Now, the more difficult part is what is happening to the graphs here. And that's a situation where if we have a curve, we're going to use our pen, or in my case, my marker, to denote what type of values I have. And in this case, I have a 0 for velocity to start with. It increases to a certain value. So I have a 0, increases to a positive value like this. And then what happens at this point? We start, now the inside of the circle is on the right, so I start with a positive and I end up flattening out and going to 0. So it actually looks like this. It's as if the velocity graph shows an upside down V. Now in this case, this shows a negative velocity, a positive velocity because it's uphill, and this shows a negative, slope, which is downhill. And that coincides with the acceleration being above and the acceleration being below for the different segments. So this curve here, which looks kind of weird, shows two distinct segments, a positive velocity increase and a velocity decrease, and then acceleration as positive and acceleration as negative. So this graph right here shows an object speeding up and then slowing down. Now finally, let's look at a graph that should be familiar to us because we did it as a practice problem earlier. This showed an object that was traveling in the Earth's gravitational pull. It was moving at a certain rate of speed, slowed down to 0, and then finally reached a negative value that was bigger than 0. So it decreased its speed and then increased its speed in the negative direction. Now, can we from this use the slope to get an acceleration graph? And if you remember, the slope of this is constant. It's all the same value, and it's negative. So the acceleration should be over here, underneath the axis. And the reality is, if this is actually in the Earth's gravitational pull, it should be 9.8 meters per second squared. We should get the acceleration of gravity. Now the question is, can we recreate the displacement graph from this? And that's a little trickier. You probably wouldn't be asked to do this on an assessment, but I think it's important to try and practice. So if we practice harder problems during class, when we get to an assessment, they should seem easy. Now, this shows a positive velocity approaching 0. And we know it has to be a curve because it's accelerated. And in fact, both segments need to be curved. But remember, this is a negative acceleration. So in order to do the cup test, it has to be downhill. Now, a cup can be downhill like this, or it can be downhill like that. And the reality is, those would both be negative. So this actually shows a curve like this, and then a curve like that. So the path of the ball, the parabolic path of the ball, represents this velocity versus time graph, which then represents this acceleration versus time graph. So if you toss an object in the air and catch it, this is the displacement graph it should make, this is the velocity graph it should make, and this is the acceleration graph it should make. And this would be a great thing to analyze using video analysis or possibly a motion sensor where you can collect data in real time and see if the graphs do look something like